Yes, sir.
Am I audible clearly?
Yes, sir.
Sorry for the delay. There was some technical glitch because of which I could not allow you to enter into the room. So I have to reconnect everything. Okay. Sorry for this particular class, which we have to schedule at somewhat awkward time. I understand it's Saturday and 3 p.m. So bit difficult to attend this class. But since we are running behind, so it is better that we should take this class and come close to what others are. So let's move. In the previous class, we were discussing the one-dimensional defect. As the name suggests, one-dimensional defects, which is also called dislocations, they appear as if the defect is extended in one dimension. So how it appears in a solid? If you consider solid to be the periodic arrangement of atoms, then its 2D variant looks somewhat like this, which we have shown in this particular image. What you can see is on either side of this crystal lattice, you have periodic arrangement of atom which starts from the top and extend itself up to the bottom. But somewhere in the middle, you can see there is one plane which starts from the top but does not extend up till the end. So this is the region that is of our interest. This particular region is of our interest. As I said, what you are looking at is the cross-sectional view. In fact, it's a 3D solid. So there will be an identical layers, infinite number of layers, which are lying one behind the other. So what you are looking is only its side face. And there may be large number of such identical planes which is lying behind this one. So the defect site is actually present at the position which is immediately below this extra half plane. So wherever the extra half plane ends, it looks like a line, but it is not a line. In fact, it's a plane. Why it's a plane? Because you have an identical feature behind this extend to an infinite depth. So if I look at this particular edge into the plane, then you will see there is an edge below which there is a missing atom. So the region which is here into the screen is the location where your one-dimensional defect is lying. Now, many students may argue that we have missing atoms here also, we have missing atom here also. Then why we are calling only one particular site, which is this particular site, to be the one-dimensional defect, and why not we are referring, say, this site or this site as one-dimensional defect? It is because the edge of the extra half plane, where the extra half plane ends, you have highest amount of distortion. So if you look into the entire lattice, the point where the extra half plane ends, that is where the highest distortion in lattice takes place. And that is why we referred that particular location as the location of the defect and not any other position. So you can represent this particular geometry neither as an extra half plane nor as the missing half plane. Rather than we define the edge of this extra half plane as one-dimensional defect, which we referred as the edge dislocation. So this is the position where your edge dislocation lies. Okay, so what can you say is that if a plane ends abruptly inside a crystal, we have a defect. The whole of the abruptly ending plane is not a defect, but only the edge of the plane will be considered as the defect. So if you look along a plane and the edge of that particular plane is basically your one-dimensional defect. So you can consider half plane like a piece of paper, and the edge of that paper is nothing but your edge dislocation. This is a line defect called an edge dislocation. You can also understand the edge dislocation in terms of a Berger vector. Berger vector is basically a vector that defines the magnitude of shift when atomic layers shift over one another when subject to a force or load. Let's say I apply force on the top region of the atomic planes from left to right. So the red color arrow represents the direction of the force. Under this force, what you can see is plane 1, which is supposed to be at a place which I am now marking. I expect my first plane to be here, but under the influence of the force, it has migrated from its parent position from here to this new position. So your atomic plane 1 is precisely sitting on the top of the atomic plane 2. Likewise, 2 has shifted onto the third, and third one has shifted on the top of the fourth one. So Berger vector is basically a vector that represents the direction and magnitude of the shift under an applied load. Now what you can see is the shifting happens only above a particular plane. So if I look this red color line, this one, this particular one, then what you can see is every plane above this has undergone a shift, while the one that lies below it, this particular region, has not undergone any shift. So this red color line is basically the region which distinguish between planes which have shifted from their parent position and the planes which remain intact. So you can also refer this particular plane over which the shift has happened as the slip plane. So remember, whenever a solid is subject to a load, you have atomic planes shift from their parent position to a next neighboring new position, and the shift will always happen on a particular plane which is referred as the slip plane. So this is an imaginary plane happening over which now an interesting thing is the direction which this black line indicates. The black line is basically the region which is demarking your slip plane into two portions. On the left hand portion of this black line, you have atomic planes which is shifted by a magnitude which is equal to the Berger's vector, while on the right hand side of this black line, no atomic planes have undergone any shift. So the black line is basically the demarcation line between the slip and the no slip region. So remember, your slip plane always have two parts. The fraction of the part where the atomic planes has undergone a shift is being referred as slip region, while the remaining part where no shifting has occurred is being referred as the no slip region. But the plane as a whole is being referred as slip plane. The boundary between the slip region and no slip region is your edge dislocation. And always this is basically the edge of an action. Am I audible? Hello, am I audible?
Yes, sir.
Can you see the screen?
No, sir.
Now,
No, sir.
is it visible now?
No, sir.
Can you see the screen?
Still, so it's still showing that you've started screen sharing. The screen is not visible yet. Yes, sir. Now it's visible.
Now it's visible.
Yes.
Okay. So, what I have explained is under the influence of the load, the migration of atomic planes happen only on a particular plane, and that particular plane is being referred as the slip plane. The region over which the atomic planes shift over the slip plane is called the slip region, while the other part over which no shifting has happened is referred as the no slip region. And the boundary between the two regions, that is the slip region and the no slip region, is basically the edge dislocation. So what you can clearly see is the correlation between the direction of the Berger vector and the direction of the edge dislocation is your Berger vector B, and the direction of the edge dislocation, which we refer in terms of translational vector T, they are always perpendicular to each other. So this is the typical correlation between them. Your Berger vector B and the translational vector T are mutually perpendicular to each other. So in general, the correlation between B and T could be anything, but we have three special cases between B and T. When B is perpendicular to T, we have the edge dislocation. If they are parallel to each other, then we referred the case to be the screw dislocation. Remember, both of them are one-dimensional defect. And if B is neither parallel nor perpendicular to T, then we will have a one-dimensional defect which is partially edge and partially screw, which is referred as the mixed dislocation. So we have already understood the edge dislocation. It appears in the solid when a lattice plane abruptly ends in the middle of the solid, and the edge of that plane is your edge dislocation. The direction of dislocation is always perpendicular to the direction of the Berger vector. Now we are moving to the second case where your direction of the distortion, that is the direction in which you are applying the load, which is defined by Berger vector, and the translational vector, the direction in which your one-dimensional defects develop in solid, will be parallel to each other. Means your screw dislocation appear in the same direction in which we have applied the load. So let us understand this case. Okay, to understand the screw dislocation, look at this three-dimensional structure. You can consider the solid to be made up of multiple unit cells. So each tiny cube, which is marked as black lines on this image, is actually making this particular solid. So you can imagine the entire solid to be made up of multiple arrangement of unit cells. Now, to understand the exact location of screw dislocation in a solid, I urge you to focus on one of the edge of the solid. So let's say we are here. The point I am just marking now. So we are, let's say, in this particular corner. We are here. Now let's start moving from that particular edge to the right. So I am making multiple steps. You have to count from this. This is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have moved 10 steps from left to right, then I reach on the front surface. Remember, 10 steps. Now I'm going downwards from here. 1, 2, 3, 4, 5, then 6, 7, 8, 9, 10. 10 points downward. Now I am going backward. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 on the backward. And if I go again top, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So from left to right, the distance is 10 points. From top to bottom, the distance is also 10 points. That means dimensionally it is equal. Now, instead of starting at this particular corner, let's say we start from here on this particular point. So now let's start counting. We are first going downward. So 1, 2, 3, 4, 5. 5 points downward. We have already counted from front to back is 10 points. So 5 downwards and then 10 back. The up one is also 10. So 10 up, then 10 front, and now I am going downward. 1, 2, 3, 4, 5. Remember, your initially downward was also 5 and this is also 5. So total is 10. But now what you can see is your starting point and end point are not same. You ended up to a point which I am marking in blue color. So you have started at the red point and you have ended at the blue point. Whenever this happens in a closed circuit, I made a closed circuit by moving at equal distance from left to right and top to bottom. Then if your start point and end point does not match, then you can draw a vector which interconnects the new point to the old point. And this magnitude of deviation and its direction is the Berger vector. This happens in a solid if the closed circuit which we have prepared contains a one-dimensional defect like dislocation. So whenever your closed circuit, which we now call the Berger circuit, contains a dislocation, then the end point and the starting point do not overlap with each other, and the vector connecting the new point to the old point is the direction and magnitude of the Berger vector. Now, I want you to focus on one particular point on this particular entire solid. That is the point which is the junction over which the atomic planes has shifted under load and below which there is no shift. So I am just marking that particular point with a red dot. So this is the point. This is the point, right? What happens now if I apply a shear force along this direction? Along this direction. Then what happens under the influence of the shear? This particular atomic planes, the one which is along this line, has migrated over the lower region. So your lower region is basically this particular region, right? And if you look at this shaded yellow color region, the one which you can see here, I'm marking it with an arrow. This particular yellow color region. So what you can see is under the shear force, your atomic layers on the top of this yellow plane has shifted, but this time shift is half multiple integer of the atomic transition. Remember, in the previous case, the first atomic plane shifted over the second one has shifted over the third one, and third one has gone on the top of the fourth one. Here also, if I focus on the edge of the solid, which is here, what you can see is your atomic plane, which was here at red point, has undergone a shift to a blue point. So at this point, your atomic planes has shifted, which is equal to one atomic plane distance. But now if I look inward towards the origin, that is, I am looking from this point into the solid in this line, along this line, then what you can see is all those points which lies in between, which I am now marking with a blue line, they have undergone a shift which is equal in magnitude, which is smaller than the one atomic distance. Can you see? All these points has migrated by a magnitude which is smaller than one atomic distance. So all such points which has undergone a shift which is not equal to a complete translational vector, one atomic plane, then they appear within the solid at a point which is a non-lattice position. What is the overall impact? The overall impact is along the line, if I look at one particular constant radius, then all the atoms lying at that equal distance from the origin is now shifted to a position which is a non-lattice position. So now if I draw an imaginary circle which is passing through a point that is an equidistant radius r on either side of the origin, what does it mean? Let's say I am taking my radius to be equal to some value which I am marking with a red color line. So let's say this is my radius. So if I draw an equal radius in all the direction, then you can see it makes a circle where all atoms will undergo an equal amount of shift. So if I look inward into the solid along this T line, along this line, then you can see around this line all atoms arrange themselves as if they are on the periphery of a spiral. So if I look inward into the solid around this line, then you can see your atomic arrangement is modified in a way they appear to be sitting on the periphery of a spiral. So the spiral appears as a screw, and because of which we referred this particular direction as the screw dislocation. Remember, in this case, we have applied the shear force B, which is also parallel to the direction of the screw dislocation. So in this case, the direction of B and the direction of T is same. It could be parallel or it could be anti-parallel. It doesn't make any difference. If it is going, means your shear is, let's say, in the reverse direction, then B will be anti-parallel to T. In either case, your screw dislocation and the Berger vector will remain parallel or anti-parallel to each other. समझ आ रहा है? Any doubt here?
No, sir.
Okay, I request you people to read this topic because it is a bit difficult to visualize unless you read the concept. Okay, let's move to the Next one, so what we have understood here is your Berger vector B and the translational vector T in case of screw dislocation are parallel to each other. This means that the parallel planes, which is perpendicular to the dislocation line, loses their distinct identity and becomes a continuously spiral ramp. So all the atoms, if I look in any direction from the origin, vertically up or down, they move to a non-lattice position and arrange themselves on the spiral ramp. So it will make a cone-like geometry where the edge of the cone is your origin, and as you move inward, the distribution of the atoms will be on the periphery of the cone, and overall this structure is being referred as the edge dislocation. Remember, we refer the center of the cone as the direction of the dislocation. Here is the summary between edge dislocation and screw dislocation. Depending on the direction of the Berger vector, we define the edge or screw dislocation to be the positive or negative. The positive edge dislocation is the one where you have an extra half plane above the slip plane. So let's say you have your slip plane, which is like this, and your extra half plane is from the top. So it is like this. This results into an inverted T-like geometry. This results into an inverted T-like geometry. This inverted T-like geometry is referred as the positive edge dislocation. In the same way, if you have the slip plane and your half plane appears below it, it is being referred as
Sir, your voice is lagging.
Am I audible? Hello? Am I audible?
So your voice is not clear.
Okay, let's close now because
Yes.
lot of disturbance is there. We will continue to discuss this in our next class.
Sir, can you provide us with the recording of this lecture and earlier two lectures?
Yeah,
Today?
I will upload the pre-recorded lectures on our Google Drive. So up to this point, whatever we have discussed, I will upload them. Today's portion is quite imbalanced, so we will rediscuss this portion. Okay, I am closing now.